Hi, my name is Ricky Dizon, and this is my remote sensing final project video. The purpose behind this project is to explore the fundamentals of remote sensing, more specifically the design, integration, and testing of our own light detection and ranging sensor, or LiDAR for short. LiDAR sensors acquire distance and range data, and with this data, experts can map geography, improve autonomous vehicles, and even assist meteorology. Now let's rewind and talk about what is remote sensing. Remote sensing is the technology of gaining information about an object without having a sensor in physical contact with that object. Now, there are two different types of remote sensing. There's passive and there's active. For instance, passive remote sensing is where there is no self-generated radiation or light. For instance, our eyes are passive sensors, as in we take in everything that we are seeing, we are not emitting any light and waiting for a return. Now, an active remote sensor uses its own self-generated radiation. So it sends out a pulse of light or radiation, for instance a laser beam, then waits for that return to come back to the machine or the sensor. Now, you're probably wondering what type of sensor is a LiDAR sensor. Well, it's actually an active remote sensor, as it has a transmitter and a receiver. Moreover, the transmitter releases a pulse of light. That light bounces off or reflects off an object, then comes back to the receiver. The transmitter in this project will be a red line laser that will shine multiple red laser points on an object, and the receiver will be a camera that can pick up those red laser points in photos. How we calculate the distance to the target is by the set distance h from the transmitter to the receiver, the PFC, or the number of pixels from the center of the focal plane that those red line laser points show, the radians per pixel pitch, RPC for short, and also the radian offset to compensate for any alignment errors in our LiDAR. Now here we have our LiDAR. As you can see, we have a red line laser as our transmitter, an Arduino Uno powering that red line laser. Next we have a Raspberry Pi 3B Plus to be our computer for our computer vision. Then lastly, a Raspberry Pi camera to be our receiver for our transmitter. I mechanically integrated this LiDAR sensor by using a 3D printed chassis that was provided by the class. I used this because it was structurally sound and it was time efficient. Next, I mounted the chassis onto a tripod along with a battery pack to power the Arduino and Raspberry Pi. Then lastly, an old smartphone to measure the inertial measurement units for our Z coordinates. Now with our own LiDAR sensor, we will be mapping this pillar outside of the Rossboro Inn. It was constructed in 1798, making it the oldest building on campus. The pillar features a simple geometry with a base and 3 different diameters. I chose this target because it was conveniently close to where I live, so that made it easy for me to pack up my LiDAR and just walk across the street and map my target. For sensor testing and calibration activities, we first started with a LiDAR that consisted of a red laser pointer and the Raspberry Pi camera. The first calibration was to take photos of the red laser pointer on a box at known distances away. At each distance, the Raspberry Pi takes a photo of the red laser pointer and calculates how many pixels away from the center of the camera frame. Now, to aid the computer vision of this red line laser point, we provide a hue saturation value that turns the whole image into black and white relatively and really exposes that red line laser point. With a theoretical curve in blue and our experimental data in red, you can see that our data matches up fairly well
I noticed that around the 4 to 5 feet region that it matches up really well, so I know that when I go to take my data in the future, I want to stay within that 4 to 5 foot range. Not only did we calibrate with our preliminary red laser pointer, but also with our final LiDAR that incorporates a red line laser. Similar to the LiDAR prototype with the laser pointer, I set the sensor at known distances away from a wall to allow the camera to record information about the red pixels, and instead of reading manually how far away the laser pointer was from the center of the camera frame, I utilized a Python code developed by Professor and Dr. Mitchell that averaged the red line laser points together to find the center pixel distance. With these known sensor distances, red pixel distances, and a theoretical curve, we could calibrate our very own LiDAR sensor. The first test with our LiDAR sensor was to scan something in our apartment, so I chose a couple of Amazon boxes on top of a chair so it would be distinguishable. Step 1 of using our LiDAR sensor is to shine the red line laser onto our object at different IMU angles. That way the IMU angle captures the Z coordinate, while our computer vision with our camera captures the X and Y coordinates of the red line laser points. After taking each image, we run them through a Python code. This Python code first applies an HSV value to really expose those red line laser points. Next, it calculates how many pixels away those red line laser points are from the center of the camera frame. With these pixel distances and the known distance between the transmitter and the receiver, it can then calculate the X and Y coordinates of those points. The Python code then distributes all the data points into a text file. With these XYZ points, we can now go into MATLAB and utilize its computer vision tool to plot these points in a 3D cloud. As you can see here, MATLAB has successfully plotted all the points in a 3D cloud, and we can distinguish some of the features of the Amazon boxes as well as the legs of the chair. Now it is time to go out into the field with our LiDAR and scan our pillar. As far as challenges in scanning this pillar, it was surrounded by a few lampposts. However, there was a great deal of construction on Route 1 that caused a lot of ambient light in some directions. For mapping my target, I scanned 4 sides with about 35 images per scan. I also kept my distance about 5 feet away from the pillar because I knew my calibration was best in that range. Similar to before, we now take these images and apply HSV color values to distinguish those red line laser points. After going through Python to sort out the X and Y Z values and MATLAB to plot this 3D point cloud, we notice that there is some noise in our first scan. To get rid of this noise, I simply just went into the text file and deleted all points that were not within range. Finally, our noise is gone and our north side now looks more like our pillar. As mentioned before, there were 4 scans from north, south, east, and west, so we had to stitch those together in MATLAB, and I did this by brute forcing it, by just going in, throwing them all into the same point cloud, then transposing them until they lined up. And here's the final point cloud. And how well does it represent the reality of this pillar? And I think it does it pretty well. It has all the distinguishable features, such as the base and the 3 different diameters, so I'm pretty happy at how it turned out. After this, I merged all of the 3D points into one merged text file. We then imported this 3D cloud into MeshLab, computed the normals to the points, then performed a Poisson surface reconstruction to attempt to mold our pillar. As you can see, it kind of resembles the pillar, but not nearly as good as the 3D point cloud.